Now it says here section 6.8 is 2 laws but only one is valid. And there's 2 laws we're going to talk about. Again, it's the law of large numbers and the law of averages. And we're going to investigate those 2. And let's talk about this. Expected versus observed counts. Expected counts and the law of large numbers allow us to predict what happens when there are many trials of an experiment. For example, if I were to say, if I tossed a coin 500 times, what's the probability that I'm going to get heads? Well, there's a theoretical probability of getting heads on one coin is 1/2, but what is the expected outcome? If I tossed it 500 times and it showed up 200 times, then the relative frequency, what I'm going to get, will end up being 2/5 of the time as the relative frequency. But the theoretical probability for this is going to be 1/2. So if we look at the definition here of expected count, it says this. If an outcome in an experiment has probability P, then in n trials of the experiment, the expected count of the outcome it's going to be n times P. And let's just take that coin example. If the number of trials in this case, or n, is 500, I flip the coin 500 times, theory says I'll get heads 1/2 of the time. So 500 times 1/2 is 250. That's the expected count. Now the relative frequency in this case, when we did the actual experiment, again we only had 200 times of heads and we did 500 flips. The relative frequency was going to be 2/5 on that. Now I want to take a look at this example. It says a current estimate for the population of left-handers in the population is 9%. What is the expected count of left-handers in the classroom of 36? It's meant to be a very easy question. The expected count again is the number that you have times the probability. So you're just going to take 36 as our number. And the probability on this is going to be 0.09 as a decimal, which will give us 3.24. So approximately 3 people in the class will be left-handers. I want to go through this problem here quickly. You don't have this on your slide, just do it after example 1. And here's the case. On Earth, assume that the wet season is 125 days long. Okay? And it has a probability of rain is going to be 85%. Now for the other days that we have 240 days. So the other 240 days, assume that there's a probability of rain 10% of the time. Now, the question would be this. What is the expected number of days of rain per the year? So the expected number of days of rain per the year, what you can do for this particular problem is just combine the 2. You can do the total count of 125 times 85%, and then add to it the total count of 240 days times 10%. And you're going to get about 130.25 days of a full year is when we can expect rain. Now let's take a look at another example. Here it says, suppose a town has about 25,000 adults in its population. If the unemployment rate in town is 5%, and you sampled 200 adults from the town at random, what is the expected count of unemployed? Go ahead, pause the video for a second, and compute your answer real quickly. Turn it back on and see if you got it. Now what you should have gotten from this is take the 200 times the 5% and get about 10 unemployed people. And I'll tell you, this one has a little trick. It's just the play on words. They are sampling 200 adults, and it's from that sample of 200 adults they want to know how many people were unemployed. They are not asking us or telling us that we went and sampled the 25,000 people in the town. So if you took 25,000 times 5%, be cautious. In this case, they're trying to throw you off with that extra number. It's really just saying they sampled the 200 people. Okay. Now let's formally define, after we've done expected count here, go into law of large numbers. Now what the law of large numbers says is this. Suppose in an experiment an event E has probability P. So for example, the probability of getting heads would be 1/2. Then, if the experiment is repeated again and again, the relative frequency of the event will approach the probability. Here's what that says. Again, the probability of tossing heads on a coin is 1/2. That's the theoretical probability. But they're saying if you do an experiment, let's say we toss a coin 100 times and we get heads 40 times. Well, relative frequency is 40 of 100, which is going to simplify to 0.4, why this is 0.5. So the actual outcome, or the relative frequency, is not quite at the theoretical level. Now, what if we did the experiment 1,000 times? If we toss the coin 1,000 times, you should actually expect to have happen is you're going to get closer to the 1/2. So maybe this will be at like 555 times you got heads. So it'll be 0.55. So what's going to happen is the more that you do the experiment, the closer the actual outcome, which is the relative frequency, will become to the theoretical probability. And let's just look at example 2 for this case. So if we continue to look at example 2, it says here, in Kirch's experiment, assume that the coin was fair. And let me tell you about his experiment here. His experiment was this, that he tossed a coin 10,000 times, and he actually got that heads showed up 5,067 times. Okay, so here's the question. What is the expected number of heads that he'd gotten, or that he should get? Now, the expected number, if you looked at the formula again, remember, is just the number and the how many outcomes he did, and then what's the probability. So there were 10,000 times he did the experiment. Probability of getting heads is 50%. So we should expect him to get heads 5,000 times. Now find the difference between the observed and the expected number of heads. He observed that he actually got 5,067, but the expected outcome was 5,000, so the difference between observed and expected is 67 additional head flips. What is the relative frequency of getting heads? Now, relative frequency is just how many times the experiment outcome happened, which is 5,067 over 10,000 flips of the coin. So it's 0.5067 is the relative frequency. Part D, what is the difference between the relative frequency and the probability of getting heads? So the relative frequency is right here. The probability is 0.5. So the difference would be 0.0067. So this slide is just really good for understanding vocab on finding the expected number, relative frequency, and then the difference. Okay. Now we've talked about computing the expected count, and I want to go into the last part of the objective is look at the difference between the law of large numbers versus the law of differences. And there's an activity you have on the second to last page of notes, and we're just going to kind of walk through it together. What they want us to do is to toss a coin 30 times and record how many times we get heads and so forth. So let me just get a table together, and we're just going to do this very quickly together. And I'm going to need a variety of columns here. Should be good. Now what we're going to do is just simulate that we're tossing a coin. So let's say I get tails, heads, heads, tails, tails, heads, and then heads one more time. What I want to record is this, the cumulative amount of heads that I got. And then I'm going to do the cumulative relative frequency of getting heads. And then we're going to come back and I want to compute, look at the cumulative tails that I had, and then find the difference between the cumulative heads and tails. So we'll do the heads minus the tails. So I'm going to pause this real quickly and just fill in the table, and then you can just do the same if you want to record the information. Okay, if you look at what I've recorded for, actually I just did 6 tosses here. Let me just walk through it for you real quick. Cumulative heads right here has happened 0 times. Here it's 1 time, 2 times, as of here, 2 times, 2 times, and then 3 times for heads. Then I did the relative frequencies. By taking relative frequency, for example, for this one right here, what I did is we had it 2 times out of 4 tosses, so 0.5. The next one, cumulative heads, has only happened, as of the 5th toss, heads has only happened 2 times out of 5, so it's 0.4 and so forth. Then in the green, I backed into the cumulative tails. In this very first toss, we've had 1 tail. As of the 2nd toss, there's still only 1 tail. 3rd toss, 1 tail. 4th toss, we're now at a total of 2 tails. Then I looked at the difference between the cumulative tails and the cumulative heads. So here I had 0 minus 1 is negative 1. 1 minus 1 is 0. 2 minus 1 is 1, and so forth. And what I want to show you is this. We're going to compare the law of large numbers and the law of averages. So let me do this. I'm going to get rid of that. I'm going to do a quick graph of these right here. So this one right here, we're going to do, this will be the law, we'll do this the law of averages, and this will be large numbers. Now, what the law of large numbers does is it has us compute, look at the difference between, assuming that this is the probability. The general probability of getting heads on a coin is 0.5. So this line here represents 50% of the time. And they just want us to record the relative frequency. So if we take a look at this, what you're going to see is this. 0% on here for the cumulative, we're going to graph here the cumulative relative frequency. If this is 0.5% right here, 0% is above it. We're working our way down. What's going to happen if we're at 0% here, you're going to notice we're going to go to 0.5 on the next one, and then 0.6, and then 0.5, and 0.4, and then 0.6. And what you're going to see happen is this. Is that the law of averages in general is going to end up whittling its way out and working its way toward the green line. It may go high, it may go low, various shapes. And that's the law of large numbers. The law of large numbers, again, is looking at the theoretical probability, which is the 0.5, with respect to the relative frequency, which is kind of like the real probability, I guess you might say. And we graph that. So the actual real relative frequency, or the real probability, is going to work its way toward getting closer to the theoretical probability. Now, on the flip side, the law of averages, it actually looks at this right here as the difference between the heads and the tails. And what it would do, the law of averages would say the difference between heads and tails is going to be 0. They're going to put it right here. Then they're just going to graph the difference. So maybe we have -1, then we're at 0, then we're at +1, 0, -1, 0. What's going to happen is the law of averages, you're going to see bounce back and forth. Because the law of averages comes from this. What are you going to average out that the difference is between heads and tails in terms of the cumulative count? If you look at the graph on the lower half here with law of averages, it bounces up and down. It never really starts to work its way toward the actual theoretical probability. So what you want to get from this is that the law of large numbers is an actual mathematical theory. And it basically just says that the relative frequency will work its way toward the theoretical probability the more an experiment is done. And that's exactly what we would see, is if we continued to do this experiment right here, and if we looked at cumulative heads, and we did relative cumulative frequency, we would find that if we did this experiment 100 times, the cumulative relative frequency would work its way to 0.5. We would see that this blue graph would work its way toward the green line. Okay. On the flip side, the law of averages is why you can't say when you're flipping a coin, oh, it's got to be heads the next time, because that's what the average says. It's going to average out. It may not average out, because the averages is the difference between the cumulative heads and the cumulative tails. And you just bounce back and forth, because you might be high by heads 2 times, and then low by tails 2 times, and then high again, and then hit 0. It just bounces itself back and forth and never converges toward the actual 0. It'll never converge toward 0, which is this middle line right here. People tend to think, well, it'll average out to be 0. Well, it really doesn't. But when we talk probability, it does, but not necessarily with count, because we can always bounce up and down, so the average will never come out to 0.